Alright, section 4.6 talks about many different types of problems, but we're only going to focus on two of them. The first one being exponential growth, which typically talks about population of certain animals in nature. And then the other one is radioactive decay. It talks about a certain object becoming less and less as it decays into half of what it was, and that's called a half-life. So n of t equals n sub 0 times e to the rt. N sub 0 is anything with a 0 as the subnotation means the initial amount. So the initial population, meaning if you're talking about a deer population, it means the number of deer at the start of your problem. And then n of t is how many deer you'll have after t amount of time. R is your growth rate. It's it's a percentage, so you're going to have to divide it by 100. And t is time. It isn't always years. It can be hours or minutes or even seconds based on the problem you're dealing with. Radioactive decay is m of t is the amount of material you have after time t. M sub 0 is the amount of material you start with. It's times 2 raised to the exponent negative t over h. T is time. It doesn't have to be in years. It can be in all sorts of different units of time. H is your half-life. H is how long it takes for the amount of material to become half of what it was. And that's called a half-life. Alright, so let's look at question 5. It talks about a beaver population. And it says it's estimated that a certain population of beaver has a growth rate factor of 12% per year. And the population in 2005 was 12,800. Find the function n of t equals n sub 0 e to the rt. That models the population t years after 2005. So at the start, in 2005, we're told how many beaver we have, and so that's our n sub 0. And we know what our r is. They tell us it's 12%, so r is 0.12. So you can plug in for n sub 0 what it is, and plug in for r what r is, and now you've got your equation that will tell you the population of beavers after t years. So now they say, how many beaver will there be in 2010? Well, that's how many years after 2005? It's 5 years, so t equals 5. You plug in 5 and you multiply that out. Round it to the nearest whole number. Okay, and then C says how many years will it take for them to reach 50,000 beavers? So 50,000 is your n of t, and you got to figure out what t is. So you got this guy, and the unknown is your t. Divide by 12,800. Then take the natural log of both sides, and when you do that, you got log base e of e to a power equals just the power. And then you can divide by 0.12, and you get 11.35 years for them to grow to a population of 50,000. And then they ask you to sketch it. So they ask you to sketch it from year 2005 to year 2020. Remember, t equals 0 is year 2005. So this is 2010, 2015, 2020. So if you're graphing it from 2005 to 2020, you're graphing it for t equals 0 to 15. And if you look at your graph, it goes up to about 75,000 at t equals 15. So I graphed it from 0 to 100,000. And that's what my graph looks like. Number 7, it says a population has a growth rate of 3%. The government is trying to reduce the growth rate to 2%. They say the population in 2011 is 110 million. Find the projected population for the year 2036 with a growth rate of 3% or a growth rate of 2%. So your starting amount is 110. It's in millions. And they want to know 25 years after 2011 to 2036, that's t equals 25. And for part A, your growth rate is 0.03. So your n sub 0 is 110. Your r is 0.03. Your t is 25. And so you're calculating n of 25. And you multiply that out and you get 233 million. Now if you do the same thing with the growth rate of 2%, you plug in the 110 for n sub 0, you plug in 0.02 for r, and you plug in 25 for t, and you get 181 million. So a growth rate of 2% gives you almost 52 million fewer people in the country. Now 11, they're talking about the deer population, and they say the deer population, the graph shows you deer population between 2010 and 2014. Assume the population grows exponentially. What was the deer population in 2010? Well, right here it's at 20,000. So in 2010 you had 20,000. Okay, and then 2014, 4 years later, you've got 31,000. Okay, so first off, you know when t is 0, that tells you what n sub 0 is. It's 20,000. Your starting population is 20,000, so n sub 0 is 20,000. And you don't know what r is yet. We know that after 4 years we have 31,000, so you can plug a 4 in for t. You don't know r. You know n sub 0 is 20,000, and you know 4 years later you'll have 31,000, so 31,000 for n of t, 4 for t, 20,000 for n sub 0, and you can solve this for r, and then you'll know what your growth rate is. Divide by 20,000, then take the natural log of both sides. So log base e of e to the 4t is just 4t, and then divide by 4, and you get r equals 0.1096, which is a growth rate of 10.96%. Okay? So there is your equation now with the proper growth factor of 0.1096. And then part C says what's the population in 2018? Well, that's 8 years after 2010, so you plug an 8 in for t and you get this. And then say how long will it take to reach 100,000? Well, 100,000 equals the 20,000 equals the formula, with the unknown being the time. You divide by 20,000. You take the log of both, natural log of both sides, and natural log of e to the exponent is just the exponent. And you divide by 0.1096 and you get 14.7. So roughly 15 years after 2010 is the year 2025. Alright, now this one says a culture of bacteria starts at 8,600. And after 1 hour, it's 10,000. Find the function that models the bacteria after t hours. So you know when t equals 1, n of t equals 10,000, and you know n sub 0 is 8,600. So you can plug in 8,600 for n sub 0, and you can plug in 10,000 for n of t, and you can plug in 1 for t. R times 1 is just 1r. Divide by 8,600 and you get e to the r equals this, and then take the natural log of both sides, and natural log of e to the r is just r, and this guy here gives you 0.1508, which is a growth rate of 15.8%. So now you know your formula because you now know n sub 0 and you know r. Okay, so then they're going to ask you how many bacteria are there after 2 hours, so you're going to plug a 2 in there. Then they're going to say how many hours until the bacteria doubles. So if it starts at 8,600, you multiply that times 2, and that gives you your y value, and you just solve for t. So let's do that here. First one, they said after 2 hours, you plug a 2 in there, and you get 11,627. Then here, when does it double? So you multiply 8,600 times 2 and you get 17,200. Divide by 8,600 and you get 2 equals e to that number. You take the natural log of both sides, and natural log of e to the exponent is just the exponent. And then divide by 0.1508 and you get 4.6 hours for it to double. Okay, and now question 14 says a culture of bacteria was 400. The count of bacteria is 400 after 2 hours and 25,600 after 6 hours. So what's the relative rate of growth of the population? Express your answer as a percentage. Well, we know 2 points of information. We know that when t is 2, we get 400. T is 6, we get 25,600. Now we don't know n sub 0. We don't know the starting population, so we have to figure that out. Okay? Well, we also have to figure out the growth rate. Well, if we plug in 2 for t and 400 for n of t, we get this guy. And we do the same thing over here. We plug in 6 for t and 25,600 for n of t. We get this guy. Now we can solve both of these for n sub 0. You can divide both sides by e to the 2r, and you get this guy equals n sub 0. You can divide both sides by e to the 6r, and you get n sub 0. And that is the same n sub 0. So you can set these two equal to each other. Okay? Now if you cross multiply, you get 400 e to the 6r equals 25,600 e to the 2r. And then divide by 400, and you get e to the 6r equals 64 e to the 2r. And you can actually divide by e to the 2r, because you got, that's just like x to the 6th over x to the 2. You subtract your exponents. So 6r minus 2r is e to the 4r. And now you can take the natural log of both sides. Natural log of e to the 4r is just 4r. And natural log of 64. Divide by 4, and now you finally are able to figure out what r is. It's 1.0397, which is 104%. 103.97, which is approximately 104%. Alright, so now you know your growth rate is 1.04. You don't know what n sub 0 is, but you can take either original situation and plug those in and figure out what n sub 0 is. So now you know time is 2 and n of 2 is 400. You got everything except n sub 0, and you can figure that one out. So this is e to the 2.08 when you multiply that times 2. When you divide both sides by e to the 2.08, you get 49.9721. So that is your starting population, approximately 50 bacteria. So now here's your formula where you now know the growth rate and you now know the starting population. So now D and E are just asking you to plug in T and figure out what N of T is, or they tell you what N of T is and figure out what T is. So D says how many bacteria after 4.5 hours. So you plug in 4.5 for T and you multiply it out. E says how long will it take for them to create 50,000 bacteria. Well, 50,000 equals that, and you're solving for T now. You divide by the 49.9, you get this, and then you take the natural log of both sides, and when you take the natural log of e to the exponent, it's just the exponent, and then you divide by 1.04, and you finally get 6.6426 hours for it to reach 50,000.